Hello and welcome back to the Cracking FAANG YouTube channel. Today we're solving Leetcode problem 1340, Jump Game 5. I have not made one of these videos in a long time, so hopefully I'm not too rusty. Anyway, let's read the question prompt. Given an array of integers and an integer d, in one step you can jump from index I to index I plus x, where I plus x is less than the length of the array, and 0 less than x is less than or equal to d. So basically we have up to d jumps that we can make, or we can go in the opposite direction up to d jumps. In addition, you can only jump from index I to index j if array of I is greater than array of j and array of I is greater than array of k for all indices k between I and j, formally blah 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 blah. So essentially that when you're jumping between indices, your current position needs to be greater than all of the indices that you're jumping over. So essentially you can only jump down. You can choose any index of the array and start jumping, and then return the maximum number of indices that you can visit, and then you may not also jump outside of the array at any time. Okay, so this question is really horrible to read because of like the less than or equal to stuff, but the gist of what we want to do is basically you just want to find out the maximum number of hops we can make within the constraints. So let's look at an example, and for this one d is actually 2. So if we start here at 12, what are all the places we can jump? Well, we are constrained at a maximum jump length of 2. So we can jump to the 10 or we can jump to the 6. And remember that we have to jump to a place where our starting position is greater than the end position, and it's also greater than all of the elements in between it, right? If we had d equals like 10 or something, we couldn't jump to 6 because we can't get over the 14. So we have to basically, our starting position needs to be higher than all of the places we're either going to jump to or we're jumping over. So from 12, obviously we can go to 10 or we can go to 6. So if we go to 6, we can't really do anything because we can't go back to 12 because we, index I has to be greater than index j. So we can only jump, in this direction. So essentially what we want to do is, right, we can't go out of that, right? Because we can't go up after that. So we have to jump to the 10. So that's one hop we can make. So from the 10, we can now jump to the 6, which would be a total trip length of 2, or we can go to the 9, which would again give us a trip length of 2, or we could go to the 7, which would give us a trip length of 2. Obviously from the 9, we have a choice of going to the 7 or the 13. 13 we can't because it's higher than us, so we can't make that jump. So we go down to the 7, which gives us, a path from 12 to 10 to 9 to 7. So that's just like a basic example. And the way that we're going to solve this is, if you look at the solutions, you're actually going to see a lot of dynamic programming ones, but you guys know that we don't do that shit on this channel. And we're actually just going to solve it using a graph. So I'm going to wipe away some of this text and basically just go over the basic intuition of the graph, and then we'll code it up. This question is a hard question, so I'm not going to go too into depth and like walking you through line by line. If you're solving a hard level question, you should probably be able to follow my logic. If not, go try some of the mediums and then come back to this one. Anyway, let's now wipe away all of this text here and then just go over the basic intuition here. So we went over the basic example, and I told you that to solve this question, we're going to use a graph. And the way that we're going to do that is, obviously we're looking for the longest path that we can take. But to find the longest path, obviously that's going to be we're going to have to try all the possible paths that we can take, but we can actually be smart about this. So the first thing that we want to do is actually build a graph, right? And what the graph is going to tell us is that from every position, so every index, we're going to have a mapping to all the valid positions that we can jump to. So for each index, we have jump positions. And what we're going to do is we're going to build that graph for basically all of the indexes in our array here. So now that we have the graph, we can now basically figure out our path between places, right? And whatever is in for a given index here, we'll know basically how many places we can jump to that are valid. So we'll basically build our graph with the constraints of the problem, which is, remember, we can only jump up to d, steps at a time, and then we also have the constraints on where we can jump to. Once we build the graph with those constraints, What we're then going to do is we're basically just going to kick off a DFS from every single point here, and then just try to find a global maximum, right? So DFS. Now, obviously, we may visit a certain starting position, while DFSing from another one. So for that reason, we're going to use some memoization here, and we're just going to have a memoization dictionary to basically store intermediate results that we've seen. So we're kind of doing some dynamic programming, but we're not doing that weird one with like the arrays, like 2D arrays, and trying to do all that wild shit. Like, it's just a simple dictionary to look up your values. I think everyone can kind of wrap their head around that one. So that's really the intuition here. We just want to build a graph for each index, all of the valid places that we can go. And then for each index, we're just going to run a DFS to see what the global longest path we can get is. And like I said, we'll use some memoization along the way to save us from recomputing things. Because as you can see, from 12, when we get to 10, we'll have stored the result for 10. And then when we process 10 on its own, we can just reuse that result. There's no reason for us to then run the DFS from 10 again. So that's essentially what we want to do. Pretty straightforward. Build the graph, DFS over it, return whatever that maximum result is, and there you go. This question is more of a medium, but for some reason they're marking it as a hard. So let's now go to the code editor, type this up, and you'll see that it's really not that bad, especially for a hard question. So I will see you guys in the code editor momentarily. We are in the code editor. Let's code this up. Now we need to define some variables here. So the first one is going to be our graph, and this is going to be collections.defaultDict. We want to use a set here because we want all the unique points we can jump to. We don't want to accidentally double count something. Remember that we're using DFS plus memoization, so let's define that memoization dict. And just for some utility, let's define this variable n, which is going to be the length of our array. Now what we need to do is basically build all of the points from a given index that we can jump to. So basically we can go to the left or to the right a maximum of d times, assuming that we actually stay within the bounds of our problem here. And remember that if we're within d bounds, we need our starting point value to be greater than the value of the index that we're jumping to. Cool. So what we want to do is we want to say for I in range of n, we want to go both to the right and to the left. So let's do to the right first. So we're going to say for j in range from I plus 1 to n. And we're going to say if the array of j is less than the array of I, so basically where we're jumping to is lower than where we started from, and the absolute value between the distance of those two indexes is less than or equal to d, which is our allowed jump width, then we can say that there is a path from I to j. So we're going to add that to our graph. And if either of these two conditions are not met, we want to break because we don't want to go further to the right because then that means that we will not be following our bounds here. So either we're past our d, or remember that this is either invalid or that array of I is greater than array of k. So this will actually check for us both those conditions, or actually three of those conditions, to make sure that we're okay. Now what we want to do is we want to do the opposite. Now we want to go to the left, right? This was going to the right until the end of the array. Now we want to go to the left until the start of the array. So we're going to say for j in range I minus 1 down to the minus 1 index, and we're going to decrement by minus 1. And again, we're going to say if array of j is less than array of I, and the absolute value between I and j is less than or equal to d, then we can have basically a edge in our graph from I to j. Otherwise, we are breaking our conditions here, and we need to break out of our loops. So this will run and build us our graph. Now what we need to do is we need to, for each index, run the DFS and see what the maximum result we can get is. So we're going to say res equals 0 because we haven't found any path yet. And we're going to say for I, so we're going to try all of the indexes in range n. What we're going to do is we're going to say the result It's giving me the maximum of whatever the current result is, and we're going to call our DFS function to find that path length starting from index I, and then obviously n, we're just going to be using that as the length of the array here. And you'll see what we're going to do in a second. And what we want to do then is just return our result, and we're done. So that is the main function, but obviously we still need to implement the DFS function. So let's do that now. So we're going to say def DFS, and we're going to take in whatever the current index is and the length of our array, because we need to know when to stop. Obviously, if we've gone outside of the bounds of our array, then we can't actually go any further, right? So we're going to check that boundary. So we're going to say current index equals n. We're basically going to return 0 because obviously we can't find a path if we're outside of our array. All right, now what we want to do is we want to say if the current index is in self.memo. So if we've already seen this index, we can reuse the result. So we can return self.memo of whatever the current index is. And then what we're going to do now is we're going to say what? So for the next hop in the graph, so basically we want to go through all the points in our graph. We're going to say for the next hop in self.graph of whatever the current index is. So remember, the graph contains for our current index all the possible places we can go. We want to now try all those hops. So we're going to say that, oops, sorry, I forgot to create a variable here. And then we need a variable to basically keep track of our path length. So obviously path length is going to be 1. In the case that we can't actually go anywhere, we just stay where we are, and that's considered a path of 1. So the path that we've seen jumping between all the indexes here is going to be the maximum of whatever the current path is, and then 1 plus jumping to the next hop, right? So DFS to the next hop, and we're going to have to pass in n again. So essentially what we do is we basically just try to find the longest path from our current index, and we just keep running the DFS recursively, and we're going to store the results. So we need to now update our memo dict. So we're going to say self.memo for whatever the current index is going to equal path, and then path. And all we need to do is simply return the path, so that way our DFS can terminate, and then we can bubble it up and eventually continue forward. So let me just run this, make sure I didn't make any silly syntax mistakes. Looks fine. Let me submit this. And okay, I think the screen, yeah, okay, accepted. Perfect. So we see that the code is accepted. Now what we want to do is essentially just talk about the time and space complexity here. So for the time complexity, we basically have to build this graph. So for each of the n indices, we can go d hops, right? We can go whatever d is to the right or to the left. So that means that to build the graph, it's going to be big O of n times 2d. And the reason it's 2d is because we can go to the left and to the right, but we don't actually care about the 2 because it's a constant, and we don't care about that asymptotically. So d is just the width that we can go in either direction. So we need to multiply n times d to actually build the graph. And then from here, it's going to be the same process. In the worst case, our entire, the hops would be starting from the highest point on the right, and everything to the left of, the end of the array is actually smaller. So we can actually visit every single one. So in this case, we, again, need to just, we would visit all the points, so it should be big O of n. Yeah, so just ignore that part. So the overall time complexity is n times d, where n obviously is the length of the array, and d is this d that was given to us earlier. And for the space complexity, it's going to be the same thing. We basically just need to store the graph, so that's going to be big O of n times d. So like I said, not the most complex question. It's just one where you build a graph and then traverse over it. It is a little bit tricky to see how to set it up, but once you've seen this, this is relatively straightforward. This loop, a first grader could write this, and this DFS is a pretty standard DFS with memoization. There's nothing really crazy here. So why this question is a hard question, I don't know. Maybe just setting it up like a graph problem and then traversing is the hard part, but who cares? It's an easy win. And yeah, if you get this in an interview, should be smooth sailing. Alrighty, so that is how you solve Jump Game 5. Hopefully you enjoyed the video. This was my first one in a while, so hopefully I'm not too rusty. We will hopefully see if people like this one. Anyway, I'm rambling, so I'm just going to leave it here. Thank you so much for watching. Leave a like and a comment to help me out with the YouTube algorithm. Subscribe for more content like this, and I will catch you in the next one. Bye!